imagine this. You drop your pencil. It falls straight down. You get it, right? Gravity. Simple. Predictable. Safe. Now imagine this. You drop a particle, and instead of falling down, it goes everywhere at once. It disappears, reappears, acts like a wave, becomes two things at the same time, and only makes sense when you're not looking at it. Sounds like science fiction? Welcome to the weird, wild world of quantum physics, the science of the very, very small, where reality itself plays by rules that seem straight out of a sci-fi thriller. Quick question. If your homework existed in multiple states like quantum particles, would that make it both done and not done at the same time? Sadly, your teacher doesn't think so. Let's break down quantum physics. Simply, conceptually, and clearly. No PhD required. Classical physics, Newton's world, is the one you and I live in every day. Apples fall, balls bounce, everything is predictable. It's clean, elegant, understandable. But when we zoom in to the tiniest levels of reality, atoms, electrons, photons, classical physics crumbles. The laws stop working, and that's where quantum physics takes the stage. The first sign that something was off came when scientists studied light. Is it a particle or a wave? Turns out it's both. Wave-particle duality. Here comes the famous double-slit experiment. You fire electrons one by one through two slits. You expect them to land in two bands, right? Like tiny bullets? Nope. Instead, they create an interference pattern, like ripples in a pond. They're acting like waves, not particles. But here's the twist. When you observe them, when you set up a detector to see which slit they go through, the interference disappears. The electron suddenly decides to act like a particle instead. Your observation changes reality. Wait, what? That's right. The act of watching affects the outcome. And this isn't just a fluke. It's been repeated again and again. This single experiment shattered the wall between objective science and subjective observation. Think about that. Reality depends on you. And we're just getting started. Now let's dive deeper into the rabbit hole. Superposition. In classical logic, things are either this or that, heads or tails, on or off. But in quantum physics, things can be both. An electron isn't just in one place. It's in all possible positions until we measure it. That's called superposition. It's not guesswork. It's a fundamental truth of how quantum systems work. Until you observe the particle, it exists in a cloud of probabilities. Enter the legendary Schrödinger's cat thought experiment. A cat is placed in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector breaks the vial. The cat dies. If not, the cat lives. Now here's the twist. Until you open the box, the atom is in a superposition, both decayed and not decayed. That means the cat is both alive and dead at the same time. Yes, this sounds absurd. And it is. But it perfectly illustrates the idea of superposition, and this leads to something even more unsettling. When two particles become entangled, their states are linked forever, no matter how far apart they are. Change one, and the other changes instantly, not quickly, not eventually, instantly, even if they're light years apart. Einstein hated this. He called it spooky action at a distance. And yet it's real. We've tested it. It works. No signals, no delay. It's like having a cosmic twin. One sneezes in another galaxy, and the other says, "Bless you," before it even happens. Now pause and take that in. We're not just talking about tiny weird particles. We're talking about the foundations of reality behaving in ways that defy logic, distance, and cause and effect. But what does it all mean? Quantum physics challenges the most basic assumptions we have about the universe. That objects exist independently of observation. That time moves forward in a straight line. That cause comes before effect. In the quantum world, these assumptions start to melt away. So, is reality an illusion? A simulation? A probability cloud held together by observation? Let's not go that far, yet. What we do know is this: quantum theory works. It's the most tested theory in all of science. GPS, lasers, computers, smartphones, they all rely on it. And now we're entering an age of quantum technology. Quantum computers. Unlike normal computers that use bits, 0 or 1, quantum computers use qubits, which can be 0, 1, or both. They can solve problems in seconds that would take classical computers centuries. Quantum cryptography, secure communication that even supercomputers can't crack. If someone tries to intercept the message, the system collapses. You'd know instantly. Quantum teleportation, not of humans, yet, but of quantum information. We've already done it, across kilometers. These aren't pipe dreams, they're happening right now. And who knows what will come next. Quantum physics is not just about electrons and equations. It's about how we, humans, make sense of the universe. It asks us to be humble, curious, open-minded. Because the deeper we look, the weirder things get. But maybe, just maybe, the weirdness is the point. Maybe reality isn't something you observe. Maybe it's something you participate in. And if that's true, then your curiosity doesn't just matter, it shapes the universe. You've just taken a journey into one of the deepest mysteries of science. But how do you really understand something this complex? One of the greatest physicists of all time, Richard Feynman, said, "If you can't explain something simply, you don't really understand it." He developed a powerful method to learn and teach anything. Tap the screen now to watch the Feynman technique explained in 3 minutes and learn how to master any concept like a physicist. Remember, it's not about memorizing facts.
It's about learning to think beyond.